Welcome to AP Podcast 15.1. We've spent some time with equilibrium. We've spent some time with acids and bases. Now we're going to have a situation where we're going to combine both. We call this the common ion effect, and it's what happens when you dump some salt in an acid. So imagine we have a salt, some sodium fluoride, and of course we dump it in water, and as you guys know, it dissociates into sodium ions and fluoride ions. Well, what would happen if I had a big beaker with a solution of hydrofluoric acid? Don't care about the molarity right now, but just think about that. Now, if we think about Le Chatelier, and all of a sudden I've got these two ions floating around, the sodium and the fluoride, and I'm going to dump it into the solution. We know, if you recall, that the Ka for this is pretty small. It's like 7.2 times 10 to the negative fourth. So we know that already there's not a big driving force to disassociate. But now imagine I stick one of these two ions in there. Okay? And in this case, what's the sodium going to do? Nothing. Absolutely right. But the fluoride, now what we're going to do is we're bumping up the fluoride ion. So from our time with Le Chatelier, what is that going to do to the equilibrium? As you would guess, it's going to cause it to shift that way. So you can imagine this number, this 7.2 times 10 to the minus fourth, is going to go down even more. So that's really what the common ion is. If we were to calculate percent dissociation, and we will, you're going to find that it will lower it. Now this also applies if you have some salts with the cation of a weak base. So imagine I have some ammonia, and of course it's in water, and I dump some, I don't know, ammonium dichromate. I wouldn't do that, but let's say I want to dump some ammonium dichromate in there. Same thing, I've just increased the ammonium content, and so what happens? Causes a shift this way, and then of course we're going to make less of the product. So it's kind of interesting, but the chemistry is straightforward, and let's give it a shot. Let's do one. 1, 2. Now here's something that'll be great news to all of you. The calculations are the same as our last chapter. Oh, I didn't highlight very well. Oh, I really didn't highlight. All right, pretend I could actually highlight. Obviously I can't. But that's the good news, right? In other words, we're not going to do anything new. We're going to do the math the same way. We just have to be aware of the fact that there's that ion. So let's look at a potential problem here. Calculate the H plus concentration and the percent dissociation of hydrofluoric acid in a solution containing 1 molar HF and 1 molar NaF. So what am I going to do first for? Well, of course, I'm going to write out my equation, right? I'm going to go HF, and it's the equilibrium. It's going to dissolve into some H plus and some fluoride, right? Okay, now the good old ice chart stuff, the stuff you guys love. What kind of concentration do I have? I've got a 1.0 molar. And of the F, again, what's the sodium doing? Nothing, it's a spectator. So I've got 1.0 molar of F. And then how much H do I have right now? Well, of course I have 0, right? Good old ice chart, that old chart you guys know and love. Now, what's going to happen when this dissociates? Well, I'm going to lose a little bit of X. I'm going to gain a little bit of X. And those of you that are really good at this, I'm sorry you have to go through this, but hey, we want to make sure that everyone's on the right page. So at equilibrium, what do I have? I have 1.0 minus X. I've got some X, and I've got 1.0 plus X, right? Now that I've got that, what do? Well, of course, like the good old days, in the last chapter, I go Ka equals, and then I just, actually, you know what, I'll write it out there, just because I should. F minus, right? All over concentration of HF. Okay. And that equals, what did I say? Oh, it's right up there. 7.2 times 10 to the fourth, negative fourth. All right. And then of that of course equals X times 1.0 plus X all over 1.0 minus X. Now, because we have a very small K, what are we going to do with these X? Well, we're going to get rid of them, right? Ah, how easy math is when you can just get rid of the X like that. So, and then 1 divided by 1, this makes our X value equal 7.2 times 10 to the minus fourth. Right? So now I found out how much H plus we've generated, right? So we figured this part out, but now let's do this because this is where it's kind of interesting. Let's do the percent dissociation. Let me pick another color here because we can, right? All right, so percent dissociation equals the x value, which is 7.2 times 10 to the minus fourth, and that's over my 1 molar, right? And of course the math, love this math. I don't even have to, oops, let me put it times 100. Don't even have to work very hard. Calculator free, right? 0.072% dissociated. Now you're going, wow, okay, whatever. But if you were to look back at, I don't know, I think chapter 14, when we calculated the dissociation for this exact problem, we got a value of 2.7% dissociation. So you can see these two values quite a bit different, right? And why is that? That's because there is a common ion. So we've added some F, and it's caused the equilibrium to shift this way, and therefore the amount of dissociation is going to be less. So there you have it, the common ion effect. So like always, if you have any questions, we'll go over it in class, and I'll see you next time.